Thank you, Professor Kaya. Thank you, Mr. Chairman, for this introduction. Well, as a matter of fact, the work, I've been doing quite some work on fiber reinforced SCC during the past years, and at a certain point, the possibility, the chance came to collaborate with a company with a very nice idea I will tell you about, on using this kind of material and putting in some concepts that we can say we mutuated from the 3D printed concrete and using them for tunnel retrofitting. And with a reference to a real case study, we will see how this can greatly improve the sustainability of the application. So just to, how does it go? This way. Okay. This is a sketch of Italy. It's made like a boot, and you see we have this spine of mountains which actually make it quite difficult to go from one side of the country to the other. So we are a country with quite many tunnels. As a matter of fact, we are the first country in Europe for the number of tunnels and for the length of our highway tunnel network, about 1,500 kilometers. And more than 1,000 of them have more than 20 years. So they are infrastructures in quite some need of being retrofitted. And 210 of them are under watch because their situation is quite serious. Even more interesting, I will say, from the engineering point of view is the situation of railway tunnels, more than 1,200 kilometers that were built when the railway lines were developed in Italy, so between 150 and 100 years ago. And about 70% of them are not made of concrete because technology at that time did not foresee that. What does retrofitting a tunnel imply? This, that you have to interrupt the traffic because you need to make works, and especially if you are in high season or festivities and so on, where people move from one side of the country to the other, you have cars and people and trucks carrying freight stuck into queues. And this, besides the annoying for the people stuck into them, has a very strong economic impact. A university in northern Italy has estimated that the lack of critical infrastructure, and so the fact that we are forced to interrupt traffic because of the need of retrofitting, results into a loss in the gross domestic power of 36,000 euros per kilometer per day. It's a huge number. But also, this is something which reflects on each household, because each one of us can be affected by this, and so this results into a loss of money for each household that has been estimated at about 3,500 euros per year. Money that goes nowhere, is spent into extra cost and so on. So there is a huge need of finding effective solutions for retrofitting our tunnels in a fast, but in a structurally efficient and sound way. Well, technologies are quite common. You go into the tunnel, make some scraping to remove the damaged layer. You have to estimate how much thick is this layer that you have to remove. Then you can do with some shotcrete some temporary works, and then you can use completely cast-in-place technology, or you can use some partially precast technology. This is how we do more or less like this. And with this company, this is a startup. Actually, the idea was from one of our former students in our university. The company is called Infra. They patented, and we collaborated with them to patent this new technology. This is their main, robot, let's say. There is this scrapping modulus here, which advances, and then you have this formwork here. This is the bottom formwork of the new lining, and the existing lining for the top part. So basically, the technology, as I said, we mutuated some ideas from 3D printing technologies. What is 3D printing? You deposit in a layer a concrete, and the concrete immediately, in that case, holds its shape. So we worked out on a mix, and actually the first trials were done with this robotic arm, which was a robotic arm that was used for 3D printing. We built up this small mold, and we tried to see if we cast this concrete and it fast sets and we can move ahead this modulus. So we horizontally slip formed, in a sense, the tunnel. So with this mix, which is SCC, which has a particular mix design, which employs SCMs, but also has a fast setting, we can greatly increase the productivity of the retrofitting train, and so have a real case in which the time in which you are forced to interrupt the traffic is much, much shorter. So company prepared us this full-scale test bed. Actually, this steel structure simulates the existing tunnel, and this is the moving modulus. Basically, this is the inner formwork. You go with a pump, you cast the concrete. I will show a video then, and you then advance when it's ready. And the technology works in this way. Let's see if this movie works. So you can see this is our fiber reinforced SCC. You can appreciate here the fibers, which are clearly visible. After about 1 to 2 hours, depending on the mix, depending on the season, you can slip form your tunnel segment, which is pumped from the key. You can see this is the slip forming modulus slightly advancing. So in about 1 to 2 hours, you go from here to here. And we were able to measure the strength development from the very early ages. So this is at 4 hours, 8 hours, and then you continue with the normal hardened state measurements. Actually, tomorrow in the first session of the early age properties, I will have another presentation dealing on what happens exactly in this window here, which is where you have to take the decision, how fast can I slip form, and how can I control the productivity. But what most of all was interesting, as I said, this was a fiber reinforced SCC. So was interesting the compressive strength, but also the toughness. And we performed the toughness test starting from 4 hours. This was really the minimum time for the specimen to be demolded and to be handled and tested in 3-point bending. And you get curves like this where you identify these residual strength values at 0.5 millimeters and at 2.5 millimeters. So according to the European standard and the design codes, they are noted as FR1 and FR3, and you provide a toughness classification of the concrete based on the characteristic value of this strength and on the ratio between these two. So the first number that you see here, 3, 4, 6, means that at 4 hours, 8 hours, 24 hours, you are able to guarantee a characteristic value of the residual strength equal to 3, 4, and 6 megapascal. And you use this in the design. This letter here, E, means that this second residual strength is at least 110% of this. And so basically you have what we can call a deflection hardening or a deflection quasi-plastic behavior. And you can see these curves which were calibrated for the hardening of the material. Well, first thing that we did is after 4 hours, is this lining safe for the people to move, for the work to move throughout the tunnel, because at that point you need really the crew to go in and to do the job. And not only we checked the safety for the new lining for its own self-weight, which is what is required. But also we checked the transient and accidental situation where the existing lining can, because of any reason, fail, and so immediately transmit the wall loading also from the surrounding rocks and so on to the new lining. You see that all these black dots represent different combination of actions for the different situations that we examined, and the smallest moment axial force domain for the cross-section of the lining at 4 hours, applying all the material safety factors are recommended in the design, is well, guaranteeing the safety. Well, this was a design calculation. We then went into testing, into validating this on a full-scale mock-up that was casted. Actually, were 2 identically or nominally identical mock-up, which were slip formed according to the technology that I showed. They were slip formed in the company test site, and then they were transported into this lab, which is a lab owned by the European Commission near Milano, where we put the segment horizontal in order to apply the loading to it. This is a sketch, as you can see. We had this constraint which simulated the bottom part of a tunnel lining, and we had 7 actuators which can be commanded independently, either acting as a fixed constraint or applying a load, because we try different load combination according to the different, case studies that you can have. This was a collaborative project which was funded by the European Union, and together with the company we worked at it, also Politecnico di Torino collaborated with us. And as a matter of fact, you can see this is one of the situations. We applied the load here and applied the load here, and we got very, very nice results. These were 2 full-scale mock-ups, nominally identical, which provided a fairly repeatable response, considering that you are dealing with a 5-meter diameter lining. And the black curve is a simple model that we performed with a professional commercial finite element software. You're dealing with plastic hinge models just to simulate the response, which provided a good, fairly agreement with the experimental results. So the methodology that we proposed, obviously in the software we implemented some cross-sectional responses based on which are the recommendations of the design methodology for fiber-reinforced concrete that you can find in Eurocode 2, you can find in FIB Model Code 2020, you can find in ACI 5444R, because we implemented in that. So at this point, we were happy about that. And you can see here some of the cracks that were formed according to the test methodologies. Where does the sustainability come? It comes because we scaled up to a real tunnel. It was not a very long tunnel, it was about 130 meters long, but was on the Italian main highway, the one going from Milan, which is about here down to Rome and Naples, and this is near Florence. As a matter of fact, is the craziest junction in the Italian highway network. This concrete was 60 years old, was in need of being retrofitting. It was retrofitted with the new technologies, but we had to prove which were the sustainability advantages with respect to a traditional technology which employed the conventional reinforced concrete. So we actually studied a conventional reinforced concrete retrofitting, and these are the different, job site operation and job site stages that we have to perform. You see here, the main thing is that you need about 1.5 months over a 130-meter long tunnel in order to detail the reinforcement, to install it before going to cast concrete. Obviously, you proceed step by step, but this is the total duration of that operations. Just focus on that. When we went with our fiber-reinforced SCC, no need of reinforcement except for in the bottom abutments, you see that we went down to 15 days plus 22 days. We saved a lot of time because we eliminated most of the reinforcement, and we saved time also on the casting because of the fast setting, we were able to demold earlier. So the whole productivity of the job site went quite fast. These were the input numbers for our life cycle analysis. We used conventional software for LCA, CIMA Pro, and we limited ourselves to a cradle-to-gate, so delivering the new tunnel to the stakeholder, basically. As you can see, if you combine concrete and steel, because this is always the right way to make the comparison when you deal with fiber-reinforced concrete. Fiber-reinforced concrete already has some reinforcement inside it, and that reinforcement has an impact. Ordinary concrete does not have reinforcement, so you have to sum up that. But at the material level, already there was some saving. It was about 5%. 5% may not be enough to convince the stakeholder to go for the innovative solution. But the great saving came from the fact that, summing up the duration of the operation for the traditional technologies and their duration for the innovative one that we proposed, we have over about 8 months of duration of the job site, a reduction in the construction time of 51 days. So it's about 2 months. You have to close your highway piece by 2 months less. Well, the thing is, how can now we transform this savings, this shortening of the job site duration, into impacts, into costs? Well, methodology is quite consolidating. You have all the equipment and the machinery that you need to perform your operation on the job site. You have to estimate, you have these numbers, the consumption of gasoline, of oil, the time of the workers to operate that. So this resulted into a total reduction of the job site of 8% in terms of impacts, with different savings depending on the global warming potential. You see this is the most interesting one, and so on. So the total saving was 12% on global warming potential and even more on other indicators, which was quite enough to convince that with this technology using SCC, a mix which was targeted for lower embodied energy, a fiber reinforced SCC which helped you also to save on the reinforcement, you have this saving. The most interesting come anyway on the social aspects. Any hour that we spend in a traffic delay has been estimated value for money at about €9, could be $9.5, some US dollars, something like that. But any time that a freight truck spends in a queue on the traffic, values about €35. So actually we worked with the Italian Highway Authority on that junction of highway. Every day a number of 30,000 passenger cars and 5,000 heavy good vehicles pass through. So if you estimate an average duration of your traffic delay of 1 hour, which in some cases may be optimistic, for the total 51 days that you save on the job site, the numbers are huge. So this is something we are currently working on because these numbers have to be dealt with care. But also there is another important thing, and there is another part of the work that we are currently tackling, which is the improvement, how to say, in the accident rate that you can have if you close your traffic for less time. There are these numbers, you have to handle them with care, but surely this results into additional social benefits, social sustainability, that a better material, a better concrete, coupled with a better construction technology can allow us to do for our infrastructures. So basically, summing up, we have worked developing a low-carbon fiber-reinforced SCC, steel fiber-reinforced SCC, whose key properties were this fast strength gaining, which allowed greatly to improve the productivity of these tunnel retrofitting technologies. The life cycle assessment showed that there are interesting improvements in terms of all the environmental indicators, but what is even more interesting are the benefits that, considering the traffic and the beneficial effect that having a shorter duration of the job site and so shorter interruption of the traffic, you can have on the overall sustainability of the job site with interesting social impacts. And I thank you for your attention.
Thank you very much, Liberato, for this very interesting presentation. Floor is open if you have any questions. George.
Nice presentation. I just have a question about the fibers.
Yeah.
What kind of percentages and what
size
of
I
fibers?
forgot to mention that. In that case, we used 40 kilos of steel fibers per cubic meter, so it's 0.5% by volume.
Very small.
Yeah, it's small, but you have to consider that the tunnel lining mainly works under compression, so you have just some bending moment at the edges and so on. So that was quite enough to guarantee, as I showed, the safety, the structural safety of the...
And how long they are?
They were 60 millimeter long.
Oh, yeah. That's
60,
big.
60.
60, huh?
2 inches
Two and a half inches,
yeah.
Okay. Thank you.
Thanks for the presentation, very interesting. Just asking about the fire rating requirement for this tunnel. would it like impact the design fiber content and whatever?
Yeah, no, thank you for asking. Actually, it's something we have been working on. We developed, how to say, a portable fire lab, in the sense that we call it the barbecue, because we have something like a barbecue. We went on the mock-up of the tunnel, and we have a flame which directly hits a part of the region. Actually, the fibers have a twofold benefit. Well, one of the main risks in this case is the explosive spalling because of the fire. In our case, we had both a delay in the spalling time, which is beneficial because you have more time to evacuate the tunnel and so on. But also we have a much smaller spalling area. So this reduces very much the risk because you don't have, like to say, projectile chunks of concrete that are explosively expelled, spalled out from the tunnel lining. Actually, we proved that our material had satisfied all the fire requirements which were set by the highway authority. We experimentally proved that, yeah.
And may I ask, what was, is it 2 hours, 3 hours, like the fire rating required for a tunnel?
Yeah, I think like that, yeah. I don't remember exactly the number, but it's like, because it's a very short tunnel in this case, yeah.
I see. Was there any like analytical modeling came before, you know, the actual applying the fire on the mock-up in order to predict how this is going to behave?
There were studies done. Actually, I didn't take care of that. There was a colleague of mine in our research group who did that. They also, you know, modeled these fire scenarios depending on where the vehicle can get into flame and so on, yeah.
So there was like some sort of confidence.
Yeah. There was the modeling before, but also we proved on the mock-up is scale 1 to 2 because the tunnel is about 10-meter diameter, the mock-up is 5-meter diameter, but in the end that is the material. And we proved experimentally that the requirements were satisfied. Yeah.
Thank you very much.
Thank you for asking, yeah.
Yeah, thank you very much for very interesting presentation. And Kamal and I also try to organize another session, try in future, and see how the fiber will impact the concrete workability. Then SCC even have more than workability. So can you give a little bit of comment? You know, you do both the plain concrete and the fiber reinforced concrete.
Yeah, well, actually, yeah, it's my, you know, it seems tricky. You must have a fiber reinforced and an SCC. Well, actually, the model we developed and we always work with, it's based on the equivalent paste thickness. So we had something like you transform the fiber into an equivalent particle, equivalent aggregate based on a specific surface area, and then you're able to calculate the thickness, the equivalent thickness of the mortar, and that is the parameter controlling actually the workability. Then, as I always say, if you have a good SCC mix and the fibers, simply summing them up does not make a good fiber reinforced SCC. You have to adjust, for example, the grading of the solid skeleton, and you know, when you put the fibers, they have occupied some space, they alter the void ratio and so on. So you have to take into account all these factors. Likely you have also to modify, as Kamal was saying, SCC has a lot of paste fraction, you have to work on that side. Alter, modify, or work on the paste composition and on the paste rheology to end up with a good fiber reinforced SCC.
Thank you. Hope we invite you back for another session.
Okay, you know that I am always happy to come back.